So let's go ahead and do an example problem looking at the performance of a solar plate collector. So this figure, you have the results of a performance test for a single glazed flat plate collector. The transmissivity of the glass is given as 0.9, and the absorptivity of the surface is 0.92. For the collector, they want you to find the heat removal factor, assuming the y-intercept to be 0.8, the overall conductance, the rate at which the collector can deliver useful energy when the irradiation incident on the collector per unit area is 200 BTU per foot squared hour. The ambient temperature is 30 Fahrenheit, and the water temperature is 60 Fahrenheit. And then D, also to look at the collector temperature when the flow rate is 0. So here is the graph that they provide. They provide the efficiency on the y-axis, and the x-axis basically is a temperature in to the collector of the water entering the collector minus ambient divided by the sun irradiation. So let's start with part A. Part A is asking us to find the heat removal factor. So if you look back at this equation, again, we get that the efficiency is equal to this intercept, F, which is the heat removal factor, times transmissivity times absorptivity. So the problem statement basically gives us that that intercept is equal to 0.8. Trying to find the heat removal factor, the transmissivity is given as 0.9, and the absorptivity is given as 0.92. We can go ahead and we can solve directly for the heat removal factor, which in this case becomes 0.97. Part B is asking for you to compute the overall conductance. Now, the overall conductance can be figured out pretty much from, again, analysis on the graph. So if we get that the efficiency is equal to the intercept minus the slope times x, Tn minus T ambient divided by the sun irradiation. This ends up becoming the slope. Figure out what the slope is by looking at the change in y over the change of x. Set that equal to the heat removal factor times the conductance. You should find that the conductance is 1.03 BTU per foot squared hour. Part C is asking you to compute, again, the rate at which the collector can deliver useful energy, so Q useful. The basic definition for the efficiency would be that it is Q useful divided by the irradiation hitting the surface of the collector. So what they're asking us is to compute that if the irradiation is 200 BTU per foot squared hour and the inlet temperature is 30 degrees of the water entering, the ambient air is at 30 degrees and the water entering the collector is at 60 degrees. So if we were to go ahead and pull all that together, we would get that we have our intercept 0.8, right? So we're taking the intercept here, subtract out the slope multiplied by Tn minus T ambient over the irradiation. We can go ahead and basically compute what the efficiency is at this point. So 0.8 minus 1.0 multiplied by Tn, which is given as 60 degrees, minus T ambient, which is given as 30, divided by the irradiation, which is given as 200 BTU per foot squared hour, we can compute that to get the efficiency is 0.65, where 0.65 is equal to the useful energy from the collector divided by the irradiation, 200 BTU per hour foot squared, multiplied by the area of the collector. Again, we're going to leave this in terms of per area since you don't know what the area of the collector is. So we're going to go ahead and solve this as Q over A. We end up getting 130 BTU per foot squared hour as the useful amount of energy. And then part D is asking something interesting in this problem. It's asking for the collector temperature when the flow rate is 0, right? So when the flow rate is 0. So how do we even go about doing that? Well, I think the simplest approach, again, if we take the efficiency equation, factor out the heat removal factor, and then rewrite the equation. So give me a minute here while I do that. And I'm going to go ahead, and as I do this, I'm going to replace T in with T max. What do I mean by that? Basically, what's happening is if the collector doesn't have any water circulating through it, all of the heat is going into increasing the temperature of the collector until it hits some sort of equilibrium point. So that would mean that the temperature of the water going in should just be equal overall to the temperature of the whole, collector. So we're assuming the collector temperature and water temperature would be the same, right? So I'm going to go ahead and say, okay, well, in this case, we're looking at an efficiency of 0 because there really is no effective, useful heat coming in, right? So in that case, the heat removal factor cancels out, and I end up solving this equation then by setting the two sides equal to each other. So T alpha becomes on one side, and the slope multiplied by x goes to the other side of the equation. And I basically solve for them, and I get that the collector temperature ends up becoming 191 degrees Fahrenheit. So I hope that kind of helps clarify the usefulness of some of these parameters that we're looking at for solar collectors. And this data, basically the slope and the intercept data as given in the problem, are needed for any flat plate collector to be considered. So what you need is that slope and intercept data as well as the solar insolation data. Insolation, I-N-S-O-L-A-T-I, that word insolation is the same thing as solar irradiation. So you need basically the solar collector data compared with the basically sun data or insolation data in order to be able to analyze the usefulness of a collector at your specific location. When we look at plate analysis, solar plate analysis, for a more accurate analysis of flat plate collectors, there's something called an incident angle modifier that's taken into account. An incident angle modifier meaning modifier that kind of takes into account the angle of incidence of the sun. The incidence angle is basically the angle between the sun's rays and the normal to the surface of the collector. So in the original efficiency equation they were looking at, again called the Hodel-Willier-Bliss equation, the product T alpha, right, transmissivity times absorptivity, will change based on the angle of incidence of the solar radiation. So since most flat plate collectors are fixed and the angle of incidence will change throughout the day, basically again the angle normal to the flat plate collector to the sun's rays, the incidence angle modifier accounts for that variation by expressing the value as the T alpha is equal to this modifier multiplied by the original T alpha. So basically this modifier is expressed as a function of the angle of incidence. So again, you take this data from the solar collector, you take insolation data, and then you kind of use both in order to evaluate the effectiveness of a solar collector for your specific application, right? So basically, there's third-party certification data on specific flat plate collectors. Solar weather heating systems are available from Solar Rating and Certification Corporation called SRCC. So their website provides a PDF format, online publications for things such as, ratings for water heating systems, also a directory of different certified solar collectors, a directory of certified solar water heating systems, and an annual performance of certified systems as well, which could be used to provide an estimated annual performance for different SRCC certified systems for various locations. Here's an example of some data from a certified solar collector. So this is a sample certification from the SRCC. And the collector thermal performance rating section consists of performance metrics in both SI and English units. So you can see here different collector thermal performance ratings for clear day, cloudy, mildly cloudy, and cloudy days, as well as collector specifications such as weight, gross area, and such. And then it also, if you can go down to the technical specifications, it'll give you the incident angle modifiers, as well as the y-intercept and the slope for the efficiency equations that we were just looking at before. That data is very important to be used for analyzing how that specific solar collector will work for your application. As mentioned too, you have these collector thermal performance ratings that are split up into basically 5 different categories. So let me just take a second to explain what those categories mean. The 5 categories basically represent different uses that have one-to-one correspondences with the inlet fluid and ambient air temperatures. So this table from your book, Table 7.2, contains information defining what those categories are. So for example, category A would represent a temperature difference of -5 degrees. Again, that would be the temperature difference between the inlet fluid and the ambient air. And it gives you an idea of what type of applications those could be used for. So for example, swimming pool heating. All the way to category E, which would have that temperature difference as 80 C, and that's used for space heating, liquid system, air conditionings, and process heating and such. As with most energy system components, information on flat plate collectors is also available from the manufacturers. So that would not be a third-party source, of course. For example, the Alternate Energy Technologies website is available for information on their collector, the model AE21E. And again, they give you, length, width, gross weight, as well as the absorber coating characteristics. And so you can actually use the manufacturer's data as well. Again, as I mentioned, it's not only important to get the collector data, but it's also important to look at the sun's intensity, right? So basically what we would call solar position and insolation values. So your book contains this. You have insolation values contained as tables in your book. And these insolation values are basically sun irradiation for various times in a day. So you can see that this particular example is for a location of 32 degrees north latitude. And you can see that this is for the 21st of each month. And for the 21st of each month, it gives you the solar position in terms of altitude and azimuth angle, starting from 7 a.m. to 5 p.m. And it'll give you the sun intensity for a surface oriented normal to the sun's rays, horizontal to the sun's rays, as well as a south-facing angle, south-facing surface with an angle to the horizon of 22, 32, 42, 52, and 90 degrees. And again, these count up from 7 a.m., 8 a.m., 9, 10, 11, 12 p.m., and then counts back as 1 p.m., 2 p.m., 3 p.m., 4 p.m., 5 p.m. So in short, you can use this solar installation data in conjunction with the data published by the SRCC for specific solar collectors in order to analyze the performance of a specific solar collector. We're going to go ahead and end the video here, and we'll do the next video. We'll start the next video with an example problem.